Let's talk about empty space. By empty space, I mean the vacuum between all the molecules that has absolutely nothing in it. Or does it? There's actually no such thing as empty space. Instead, it's taken up by quantum foam. What is quantum foam? Quantum foam is made up of tiny energy waves, or particles, they're kind of both, that quickly appear and quickly disappear in the fabric of space-time. That's the thing Einstein's theory of relativity is about. The word quantum means it's on such a small scale that atoms, tiny little atoms, seem like giant solar systems. And foam just means, well, it looks like foam. Since photons, or quantum particles, like to wiggle instead of going straight, a collection of empty space looks like foam. Though we've never been able to view anything at the scale of space-time, scientists predict that quantum foam looks a little bit like this. But how do we really know it exists? After all, we can't zoom in far enough with a microscope. One of the several experiments conducted to show that quantum foam does exist was done by Casimir and is called the Casimir effect. He took two very thin, neutrally charged metal plates and put them parallel to each other at a very, very small distance in a completely vacuumed box. So no air molecules, no nitrogen molecules were in that box. It was just empty space. The results of his experiment actually supported his hypothesis, or his initial prediction. The two plates moved towards one another without any specific reason. The answer to why the two plates moved towards one another without any other external forces lies in the quantum realm. Quantum foam energy waves can be either long or short, and since the two metal plates were placed so close to one another, the longer waves could not form in between the plates. This created a greater force on the outside. Though the force was very, very small, it was there and it was enough to push the two plates together. There's actually an equation to calculating how small or big this force is. The bigger the plates and the closer they are placed initially, the greater the force will be. However, the plates have to be very, very thin so that the force of gravity doesn't push them down and they can move together just with the force of the quantum foam around them. Okay, so 99.99999% of our world is covered in quantum foam bubbles. But what can we do with them? Well, first we need to discover more about it. For example, the quantum gravity theorem, or further exploring the stuff that Einstein discovered about space and time and how they relate to one another, which is where we find the quantum foam. There's still a lot to be discovered in quantum physics. Perhaps once we understand it better, we can use it for our future innovations.